Hi, everybody. I'm Clinton Gormley. I work for ElasticSearch, and in fact, I was ElasticSearch's first user about 3 years ago. I went live with version 0.04 and have lived through a lot of bugs and improvements since then. For those of you who haven't heard of ElasticSearch or don't know much about it, it's a real-time search and analytics engine. There are a lot of buzzwords associated with it. It is distributed out of the box. Start one node, start more nodes, they form a cluster, and with that, you can scale massively. The clustering also gives you high availability, so it can survive node loss. You speak to it using a very simple RESTful API and JSON over HTTP. So this is something that you can do from the command line or from any HTTP client in any language that you want to use. It is schema-free. You don't have to set anything up to start using it. Multi-tenancy, you can host multiple applications with it, like you would expect of any database. Open source and based on Lucene. Okay, so this is all cool. But this is why we use Elasticsearch. This is the thing that makes you decide to download it, unzip it, and start it up. But then what? You've got this, you don't even know if it's up. So this talk is about getting you from zero to understanding the fundamental concepts in Elasticsearch and becoming useful with it. It's not going to make any of you an expert through this, but it'll get you a long way down the road. So how do we use it? We said we could talk to it on the command line, and the way we represent all of the interactions in the documentation and so on is using curl. And this is a very simple request. The first thing we do is specify a verb, and it's RESTful, so get, put, post, delete, head, they're the things that you're used to from any RESTful application. We'd say which node we want to talk to, and you can talk to any node in the cluster, but we're just running this on localhost, so that's the one we'll talk to. 9200 is the default HTTP port, and we specify the path to this RESTful API and any query string parameters. Now, most of this stuff doesn't change between queries, so I'm just going to show you the bits that do change. So if we just request the root path, we get a response back, and it's been pretty printed because we specified pretty. This tells you the node is up and running, the version it's at, and so on. Okay, that's cool. We have a running cluster containing one node. And I'm not going to get into clustering at all. This is about how you use it rather than how you scale it. So where do you start? Well, you've got a bunch of data, first of all. And data is represented as JSON documents. So this is a simple tweet document. We've got the content of the tweet, the username of the person who sent it, the name of the person, the date they sent it, the retweet count, and the geolocation of, in this case, me. How do you put it into Elasticsearch? You put it. You need to say where you're going to put it, and you have to specify the index, which is like a database in a traditional database. We'll imaginatively call it my app. Then, what is it? Well, it's a tweet. And which tweet is it? We'll just call it tweet1. And if you don't give it an ID, then Elasticsearch will generate one for you. But this ID is unique in this index and type. Then we just pass it the JSON body. And what I've done here, this is a curl parameter that says post this body, okay? Or in this case, put this body. And we've just thrown this at Elasticsearch. We haven't created an index. We haven't said what fields we've got specifically before indexing it. We just throw it. And we get a response back. It tells us that it has been created and gives us a bunch of metadata, which is the same things that we passed in, plus this version number, which I'll come back to a bit later. To get the document back out, it's going to be no surprise, you get it. And you get back all the same metadata, including the source field, which contains the original JSON document that you passed in. Okay, that's all good and well. We can tell it if it exists using the head API, and you don't get a body response back, you just get an HTTP response code, 200 or 404. To update it, you just put it again. This does an atomic delete and put. Okay, so you keep adding documents, and the old deleted versions get removed over time, but it's really indexing a new document. And you get back a 200 OK, 200 rather than 201 because the document already existed. The version number has been incremented to 2. To delete the document, you just delete it. And again, the version number has been incremented. So what's up with these version numbers? Well, this is running in parallel. Multiple changes can happen via multiple processes at the same time. And what you don't want to do is lose changes. Actually, a lot of the time, you don't really care. But in situations where you do care, you want to be able to control that. ElasticSearch uses optimistic currency control to do that, where it just keeps a version number that gets incremented for every change that happens, which allows it to happen without any locking. Because locking in a distributed system is a failure. So if we know which version we're wanting to update, we can specify it. And as long as it's the current version, it'll all work. If we try to update an older version, we'll get a conflict, and that change won't be committed. So at this stage, you need to handle this in your application. But it allows us to be safe about the changes that we're making. You can also update documents in place. Here's an example where we use the update endpoint, and we pass it a script, which says, increment the count field in the source document. Actually, this is doing exactly the same thing as we did before. It gets the document, it changes it, and tries to put it again. The difference is that this is happening local to the shard. You haven't got the network round trip to take into account, which reduces the chances of there being a conflict. But you can still have conflicts. And here you can tell it how many times you want to retry this process until it eventually fails back to the client. Lastly, if you're trying to make lots of changes, it's cheaper to do it in bulk. You can send thousands of log entries in a single request rather than having to pay the price of network overhead for every single request. Similarly, you want to get a whole bunch of documents back by ID, you can use multi-get to get them back. I'm not going to go into this because this isn't the interesting part of the talk. This is just how to use ElasticSearch to store your data. Most of the time, you'll have your data somewhere else already. It'll be an existing application, and you have it sitting in some other data store. And that's fine. We can work with any data store. You need to mirror the data from your store to Elasticsearch, but all can work hunky-dory from there. If you are starting a new application and you don't want to use another data store, talk to ElasticSearch directly. Up to you. OK. So now we index a bunch of docs. We've got them sitting in our Elasticsearch index. How do we search them? Let's start with the empty search. Just give me everything you've got. We get a response back that tells us how long it took in milliseconds, whether it timed out or not. That's an optional thing that you can set if you so desire. How many shards were successful? Now, I said I wouldn't go into any of the clustering or any of the distributed stuff, but it's worth knowing that an index is actually just a virtual namespace that points at a number of different shards. And these shards are where your data actually lives. And because these shards are independent, they can be moved across different nodes in the cluster, allowing you to scale out. So searching an index actually means searching all of the shards involved, getting the results back, reducing that, and then returning it to the user. So we don't expect shards to fail, but if too many nodes go down, you're going to have missing shards. And Elasticsearch tells you how many it tried to hit, how many were successful, and from the ones that were successful, it gives you the data it can. So if you do lose a shard, it's not necessarily the end of the world. You can still serve partial data. Not optimal, but it can help. Then you have the hits element, which tells us that we have a total of 14 documents in our results. There's the max score, which I'll explain in a minute, and then a list of the top 10 documents that matched our query. Each entry in this hits array gives us exactly the same metadata you've seen before, the original document, which means that you don't need to fetch it in a separate phase. You've got the whole document there already for you to display. And finally, the score for this particular document. That score says how well this document matched the query that you specified. We didn't specify a query, so all documents are equally relevant, and they all have this neutral score of 1. You can search across multiple indices and multiple types. I said that searching a single index was already hitting all of the shards in that. So searching multiple indices is exactly the same process, but extended to more shards. How you can specify it? Here you can search a single index or multiple indices, or even specify them using wildcards. And then you can limit it further to the types within those indices, or multiple types, wildcarded types, or all types, or some types in all indices. So it's up to you how you combine them, but this is what the paths would look like. We get you the top 10 results by default, and those top 10 results are sorted by relevance normally. But if you want to page through to the second or third pages, you can use size to specify how many results are in each page, and from how many results should be skipped before we start returning. So our page size is 5. Pages 1, 2, and 3 would start at from 0, 5, and 10. Okay, this is all pretty simple. Now about specifying queries. We have something called search light. Well, at least that's what I call it. And search light is pretty simple. We can specify the query in the query string, and this query simply looks for the word John in the name field, and we get results back. Search light can actually be pretty complex. This one says the word foo in the tweet field must exist, the word John in the name field must exist, and the date field must be greater than the beginning of May. That's all well and good. Unfortunately, this is passed in the query string. So once you encode it correctly, it's slightly less readable. It's also quite fragile, because this is a mini language, and if you get the syntax wrong, you'll get a syntax error. So this is not what you should be using to run your queries in production, okay? This is a development tool that you can use from the command line to do something quickly and easily. And it is useful for demonstrating things as I'm about to do, but it will come to what you should be using in production later. So here we're searching for Mary, but we haven't specified a field. We get back a user whose name is Mary, tweets sent by Mary, and a tweet mentioning Mary. So what's happening here? Well, it turns out that when you don't specify a field, it uses the default all field. And the all field is this field that is sort of magically added when you index documents. It takes the string values from all of the other fields and sticks them in here. Again, a really useful feature for starting out. Later on, you're going to want to search specific fields with the exact things that you want, but this allows you to explore your data quite easily. But there's some oddities when we try some of these searches out. If I search the all field for 2013, I get 12 results. Fine. If I search for the specific date, 2013-06-03, I still get 12 results. But I know that my data has only got one tweet on each date, so that seems wrong. If I search the date field for the same date, I correctly get 1 result. But if I search it for 2013, I get 0 results. Okay, so something is weird here, and it's worth understanding why this happens. It is due to some difference in data types. So let's look at what the data type is. How are our fields defined? And to do that, we check the mapping. Here we get the mapping for index myapp type tweet, and it gives us something like this. There's a lot here, and I'm going to be coming back to the rest of it, but the important thing to look at here is that the date field has been recognized automatically as type date. We know the all field, although it wasn't mentioned, is type string. So there's a difference between how dates and strings are handled, which kind of makes sense. You might expect that. But it's actually more than that. It's the difference between exact values and full text. Exact values are what they sound like: whole numbers, floats, dates, booleans, and they can be strings as well, where capital foo is different from lowercase foo. And full text is the kind of thing you'd have in the tweet content, in an email body, in a book, a document like that. In full text, you expect to be able to search within the text. You seldom look for the whole exact value. You want to find brown fox. If you search for foxes, you want search to understand your intent. So foxes should still find fox. Jumps should find jumped. How do we support this? This is handled easily by traditional databases. This is the territory of search engines. We build a structure called an inverted index. And the inverted index is the thing that makes full-text search fast. So there are a number of phases in it, and we'll use these two documents as an example. First, we separate each string into words, or terms, as we call them. Then we created a sorted unique list of these terms, and then specify which document contains each term. And you end up with something like this: sorted list of unique terms and the document occurrences. Now a search becomes quite easy. A search for quick and brown means we just look at those two terms. Document 2 has 1, document 2 has 2, document 1 has 1, so document 2 is likely to be more relevant. Cool. But now this search, which says you must have quick and you must have foxes, gives us no matches because we have quick in one document and foxes in the other document. No document contains both. But that doesn't seem right. Both of those documents look pretty related. So we need to improve how we are indexing these terms so that we can improve recall. Case shouldn't matter. Capital quick, lowercase quick, same thing. Same for the. So we'll merge those. Dog, dogs, fox, foxes, they're the same root word, same intent. We'll just index the root word, dog and fox. Jumped and leap, well, they're the same idea. They're synonyms, so we'll just index both of them as jump. Suddenly we have a more compact index that is better able to serve our search requests. This normalizing of terms is very important. But our query still doesn't match. We don't have the capital quick in this index, and we don't have foxes in this index. So we need to normalize the terms in the query too. The terms in the index and the terms in the query need to go through the same analysis process because you can only find what is actually in your index. Quick becomes lowercase, foxes is stem into fox, and suddenly our query works. This process is called analysis, and it consists of the tokenization into separate terms and the normalization of those terms. And this is handled by analyzers. And analyzers are just a package which consists of a tokenizer and 0 or more token filters. And there are a bunch of analyzers that come built into Elasticsearch, the default of which is called the standard analyzer. This starts out using the standard tokenizer, which divides these words according to an algorithm from the Unicode Consortium into what we think are separate words in pretty much any language that you can throw at it. Then passes through the lowercase filter, and then it applies the stopwords filter. And we don't know anything about what language you're using, so we apply the English stopwords by default. That removes those. There are also a bunch of language-specific analyzers that come built in. So the English analyzer has the same tokenizer lowercase filter, but then it can use the English stemmer to convert jumped to jump and apply the list of English stopwords. Similarly, if you're using the French analyzer, the Spanish analyzer, it would apply rules appropriate to that language. You can also use these tokenizers and filters to build your own custom analyzers, and we'll come to an example of this later on. So back to why we have this data mismatch. We said data is type date, all is type string. So that means that data is an exact value, and the all field contains full text. Date contains that exact date, and the all value contains three terms, string terms on top of that, 2013, 06, and 03. So a search for 2013 in the OR field matches that term. Searching for that date is actually searching for any of those terms, which also match. The searching for the exact date in the date field correctly gets you one result, and searching for this exact date doesn't give you any because that exact value does not exist in the date field. Okay. So field mapping is important, understanding how your data is being indexed and telling Elasticsearch about your data so that it can index it appropriately. There are a list of core field types that are supported by Elasticsearch: string, date, numeric, floats, Boolean, and object, which is like object hash map, associative array, depending on the language you're used to. There are a number of others, a couple of which we will touch on later on, but this is what you're working with. When you throw a new field at Elasticsearch, it uses dynamic detection to try to guess what that field contains. So if it looks like a string, well, it's a string, unless it's a string that looks like a date, in which case it's a date. Whole numbers become longs, floating points become double, Booleans become Booleans, and objects are mapped as objects. We haven't mentioned arrays, but there's no special mapping for arrays in Elasticsearch. Any field can contain multiple values. So it just takes the type of the first element in that array and uses that to figure out what type of data that field contains, which also means that you can't mix data types in an array. An array is a list of the same data type. By far the most important setting for field mappings is the type. And for exact value fields like date and long, generally you don't need to touch it. That's the only thing you care about. Here we can see that our geolocation has been incorrectly interpreted as an object. And that's the first thing we should fix. This is not an object. This is a specific type that we want to index. It's a geopoint. So we're going to change that to type geopoint. When looking at string fields, we need to distinguish between full text and exact strings. And we do that using the index parameter. There are three options for it. The default is to set it to analyzed. In other words, string fields are treated as full text by default. If you don't want that to be the case, set it to not analyzed. And then it will store and query the exact value. If you don't want it searchable at all, you can set it to index no. It'll still be available in your source document that you've stored, but it won't be searchable. So our nick is not full text, it's a username. Let's change that to a not analyzed field. For analyzed string fields, there's one more important setting, and that's which analyzer to apply. So we can say that our tweet field, we are indexing English tweets, so let's apply the English analyzer to that field. Okay, we've got our mapping that we want to use. How do we go about changing it? You can add new fields to an existing mapping using the mapping endpoint. So index type mapping endpoint, and then you can specify the new fields that you're wanting to add. You can't change existing fields because the data that's already in the index comes from the old settings. So you'll probably not be able to search your data properly if the settings change. So you need to re-index your data. Delete the existing index, create a new index specifying the new mappings, and proceed to fill it up with data again. This sounds like you can't store anything in Elasticsearch, but actually there are very easy ways to copy data from one index to another and have your application be blissfully unaware that anything has changed. On to full body search, and this is what you should be using for your search. This is the powerhouse of Elasticsearch. It's called request body search because you pass it a request body, and you can pass parameters like the pagination parameters and the query that you want to run. And this structure is called the query DSL. It's a rich, flexible query language that can do anything that SQL could do and more. So to start off with the basic, that your first kind of go-to query, the thing that you should use on any field is the match query. There are lots of others, but this is a good starting point. And this is saying, find the word search in the tweet field. Match knows that the tweet field is analyzed with the English analyzer, and so it will analyze the search field, maybe the query string, before searching in the tweet field. If you were to search the nick, it would know it's not analyzed and treat it as an exact value match. You pass this to the query parameter in the search API and get your results. The query DSO actually consists of two parts, the filters and the queries. And they're very similar in nature, but they have different purposes. Filters only do exact matching. Queries do as well, but they also do full text search, and that's what they specialize at. Filters just tell you yes or no. The document either matches or it doesn't. There's no other information about it. Queries are more subtle. They go, well, yes, this document matches, but this document matches better than that one. It gives you a relevance score, which it has to calculate. Filters tend to be fast, and queries generally tend to be heavier, not least of all because they have to do the relevance scoring. The output from filters can be cached, which makes them really fast to reuse, and queries can't be cached. So generally, you want to use queries for full text search or anything involving scoring, and filters for everything else. Okay. So we've got our query. Now we want to limit it only to tweets by Mary. So we're looking for the exact value at Mary in the nick field using the term filter. How do you combine these? The query parameter in search only accepts one argument. So you have to wrap this somehow into a single query that accepts both of these things. And that query is called the filtered query. And it takes a query and a filter parameter. Then you can pass that query, the filtered query, to the query parameter in the search API. Perhaps you want just a filter. Just give me tweets by Mary. Well, that's equivalent to specifying a match all query. And in fact, you don't need to specify at all. It's the default. But if I'm searching for Mary's tweets, there's no relevance. It's just I'm given a bag of tweets. To have them ordered, perhaps recency is a useful ordering. So we can sort by the date field. Perhaps I want to limit it just to tweets from the month of May, and I can use the range filter here on the date field to specify lower and upper bounds. So far we've looked at finding individual documents, but Elasticsearch is also good at zooming out and giving you an overview of what is in your index. And these aggregations, these summaries, are called facets. In this particular case, we're looking for our top tweeters. Who are the people who have sent out the most tweets in our, from the data that we have in our index? And for that, we use the terms facet, and we basically bucket by the values in the nick field. So every time we have a document tweeted by Mary, the count for Mary gets added up. And this will give us our 10 top tweeters. We can combine it with a query. So who's tweeting about Elasticsearch? These facets are calculated over the documents that match this query. And to be clear, we could have billions of documents, and this is still calculated within milliseconds. This is massive scale. Perhaps we want to count the number of tweets we have in every month. And for this, we can use the date histogram facet. And we look at the date field and take each date and slot it into a month. So now let's put some of these things together. We mentioned a lot of concepts. This is one that people often want to do. How do I do autocomplete? Somebody starts typing in a name. I want to suggest things to them. So they type in JOH, and we'd like to give them Johnny Smith, Johnny Depp, Lyndon Johnson. The only problem is that JOH doesn't exist in the index. And if it's not in the index, you can't find it. OK, so we need to index partial words. Engrams are like a window on a word, and you specify an engram of a particular length. So an engram of length 1 would just give you each word. each letter. Length 2, you'd move letter by letter, and it'll give you 2 letters at a time, and so on. This is good for partial matching, but it will match anywhere within a word. What we need for this, for our particular requirement, is edge engrams that are a specialization of engrams. They are anchored to the beginning of the word. So John Smith, as edge engrams, would produce these tokens. And that is perfect for autocomplete. Now, it takes a few steps to actually get this implemented, but we'll go through it bit by bit. The first thing is that we need to pass our terms through an edge engram token filter. So each term will get broken up by this edge engram token filter into something that looks like this. We specify, and I'll show you how you put all these chunks together later on, but first in the filter section, we call this our autocomplete token filter. It's type edge engram, and we want lengths of anything from 1 to 20 characters. Now, we apply analyzers to fields, so we need to specify which analyzer we want to use. First, for the name field, you don't really want stop words. AA Milne would have the A's removed, which doesn't make sense for a name field. So we're going to have the name analyzer, which just uses the standard analyzer, but then we'll configure it to not use any stop words. For autocomplete, we'll have the name autocomplete analyzer, which is a custom analyzer. We still want to use the standard tokenizer and the lowercase token filter, but we add in our autocomplete token filter at the end of that. Now we have to tell Elasticsearch which field to apply this to, and we do that by changing the mapping for the name field. We're using the name field for 2 purposes, ordinary name matching and this autocomplete. And to use a single value or a single field for multi-purposes, we change it to a multi-field. And we give it the 2 subfields that we need to use. This name field, which has the same name as the top-level field, is called the main field. And it can be referred to by the top-level name or as name.name. And for that, we just want to add the name analyzer. For autocomplete, it's a subfield, and it can only be referred to as name.autocomplete. And this is a little more complicated. We said earlier that you want to apply the same analyzer at search time and index time, but in this case, you don't. You want to store all of the engrams in your index using the autocomplete analyzer, but when you search for JOH, you only want to search for JOH. You don't want to search for J, JO, JOH. And so we'll use our standard name analyzer at search time. We delete the index and create a new index specifying our analyzers and filters in the settings section and our new mappings in the mapping section. And now, after we put the data back in, we are ready to query it. And the query is this simple. We search the name.autocomplete field and pass in whatever the user has typed in, and that is going to match. But John will also match Jonathan. So if we want to score whole word matches better than partial matches, we will actually want to run 2 queries, one against the autocomplete field and one against the normal name field. So the way you combine multiple queries is using a bool query. And bool queries take must, not, and should parameters. Clauses that must match, clauses that must not match, and if these match, then it's a better match. It's more relevant, but they don't have to match. So we put our autocomplete into the must match column, because if the autocomplete doesn't match, then nothing's going to match. And we do a simple match against the top-level name field in this should clause. And this now gives you a nicely weighted autocomplete function. If you just match the partial field, this clause will be scored, but any whole word matches will be bumped up in relevance. So I've lost a slide. Okay. That was the end of the main section, and I've got a few more sort of common examples that I can show you. I'll put them in as extras because I didn't want to go over time, and I think I've got 5 minutes left. 10 minutes, perfect. Okay. Perhaps we want to rank frequently retweeted tweets higher than tweets that nobody cares about. So we want to take the value of the RT, or retweet, field into account. Here's an example where we can do a query on the tweet field and then use a script to just tweak the score for that document based upon the value of this retweet. We don't want to completely overwhelm the score that's come from the main query. This is just an adjustment. So we can take the value of the retweet field, and we can use this sort of smoothing function so that it doesn't overwhelm things, and just multiply it by the existing score from the query, and we'll get a slow boosting of popular tweets to the top of our results. That was the slide I was looking for. Perhaps you want to show tweets that are only within 100 kilometers of Berlin. Well, we've got a geolocation field in our tweets, so we can apply the geodistance filter to it. Here, find everything within 100 kilometers of this central point, which happens to be this room, or close enough. Or perhaps you don't want to exclude the things that are outside that 100 kilometers. You just want to give more importance to the ones close to Berlin. And we said that queries are used for relevance and filters are used for scoring, but there is an efficient way of using filters for scoring as well, and it's called the custom filters score query. First, it runs our query, and then it looks at any filters we specify. And if the document matches those filters, you can adjust the score accordingly. So in this case, we're using the same geodistance filter, and we go, yeah, if it's local, just boost the importance of this thing a bit, and that'll increase the relevance of local tweets without completely excluding those from outside. And that's all I've got for you. I hope that this has given you enough to at least get started, to find your feet and go from not having any search to being able to do the simple things easily. Any questions?